The next step for us in resolving any degeneracy in the configurations is to consider spin-orbit coupling. Now, this is typically smaller than the electrostatic interaction, but it is still enough to split each of the terms, the spectroscopic terms that we've developed, into an additional level, which is given by the total angular momentum. So let's see how this works. So we're going to be considering the total angular momentum. J, which is of course the orbital angular momentum plus the spin. And we recall that a spinning electron has a magnetic moment. And its magnetic moment in the classical simple model, where we have an electron that's spinning here, the classical magnetic moment is given by mu equals to the current times the area over the speed of light. And we take into account an angular velocity, which is equal to 1/2 h bar equals mv r, or in the case of the speed of light, mc/r. And we can take from that to work out that the classical magnetic moment, as in the non-quantum, classical magnetic moment is equal to -1/4 E, that is the electron charge, h bar over mc. Now, if we recall that the spin is just a number that we define to be 1/2 for an electron, then we could write that classical magnetic moment in terms of the spin, and it would be mu equals -1/2 times E h bar mc times the spin. And it turns out that the quantum mechanical magnetic moment is very similar. It's given by mu E equals -1/2. Let's write that better. Mu E is equal to -1/2 GE, which is a Landé G factor, and that's equal to 2 for an electron over mc times spin. And so you can see that that's very similar. If GE is equal to 2 for an electron, then they're the same as the classical magnetic moment to within a factor of 1/2. And you can also write this in terms of mu B, which is the magnetic Bohr, the Bohr magneton. And mu B is just E h bar mc. Okay, so we know that electrons have a magnetic moment. So what can we do with that? Well, recall that if you have a magnet in a magnetic field, then the magnetic moment times the magnetic field, done with the magnetic field, gives you your magnetic force. Okay, so from there, let's consider that the electron, just take aside for a moment its own magnetic moment, and consider that the electron is moving in an electric field. So the electron is moving in an electric field, which of course, this electron moving inside an atom orbiting around the nucleus is feeling the electric potential of that nucleus. So it is moving in an electric field. And that means that it sees a magnetic field. So now we've got, fairly simply, an E cross V situation, and the magnetic field in that arrangement is minus V cross E over C, which of course we all know. So now we think about it, we've got an electron which has its own magnetic moment. It's moving through an electric field, and so therefore it sees a magnetic field. And so now it's going to have some magnetic effects. So let's consider what those magnetic effects are. Well, remember that the electric field is just the gradient of the potential, which in this case we've defined as just a radial potential. So, and if we remember that the electrostatic potential energy, UE, is equal to E times V. And of course, remembering that the orbital angular momentum is mv cross r, then we can work through to show that the magnetic field in this electron situation is just mcr dv dr, which is related to mecr due over dr. Okay? So that shows us that the change in energy for an electron with a magnetic moment, mu E, and the magnetic field, B, is equal to the Landé G factor over 2 times m squared c squared s dot L over R du dr. And that is spin-orbit coupling. So we can see that S dotted with the angular momentum produces an effect which changes the energy level of a particular electron configuration. So spin-orbit coupling is what that's called. So recalling once again that J is equal to S plus, I'm going to write it as a little l now, but it's the same idea. We can work through to get S dot L is equal to H bar squared on 2 times the product J minus, or J plus 1 minus L plus 1 minus S plus 1. We sub all of that in to find that the change in the energy state, so the separation of energy levels and the fixing of our degeneracy, is given by H bar squared GE, but that's the Landé G factor, 2R m squared c squared times this big product of J's and L's. And there's a du dr. So what this results in is an energy splitting of a given level. So we can imagine an energy split the 2p 1/2 or 3/2 level, where again, remember we're writing this p is the SPDF terms, and the terms down at the bottom refer to our J. So the 1/2 or the 3/2 are our two J components. So this actually splits this particular energy level, the 2p energy level, can be split into an energy level which is the 2p 3/2 or the 2p 1/2. And they have an energy separation between them. This produces what's called fine structure. And the energy separation between them is what we've just defined in the previous slide as delta E. It turns out that delta E is on the order of 1/m squared c squared h bar squared over the radius of the n level times E of that n level. And recall, if we were talking about something that was just, say, a hydrogenic atom, recall that for the hydrogenic atom, we defined the energy level of n, where it's the principal quantum number n, to be 1/2 alpha squared, which is the fine structure constant, times mc squared over, oops, that's n, not h, over n squared times z squared. So we're able now to see how we can split energy levels based off of their spin-orbit coupling and the total angular momentum. Now, these splits can result in things like doublets that are very easy to see, like the sodium doublet, or very common other doublets of lines. And when we go to start talking about the actual atomic transitions, which is the point of this full series of lectures, we will move into talking about these fine structure lines and how they can be used to identify particular atomic lines. And that will be a future lecture.